The final notes that I want to write with regards to an electrochemical cell relate to a shorthand notation we can use to describe a cell without having to draw everything like this. And we call this shorthand line notation. Line notation. And the first thing I'm going to do is just show you the general format of how we write it, and then we'll make more sense of these notes we're about to write by applying them to the cell that we've been referring to throughout this topic. The first word I'm going to write is electrode, but I'm going to leave some space above it so that I can write more notes above. So electrode. And then I'm going to draw a straight line, and then I'm going to write other chemicals. Other chemicals. We call this straight line a phase boundary. Phase boundary. It distinguishes between species in different phases. We'll just write species in different phases. Species in different phases. And then we'll write a note that won't make sense until our next example. Use comma for species in same phase, like aqueous. Use comma for species in same phase. Parentheses, like aqueous, AQ. And I'll note that everything we're discussing right now applies to the negative terminal. Negative terminal. In other words, right now we're talking about the electrode and other chemicals that are ultimately hooked up to this negative wire here. Ideally, this would be the negative electrode, i.e. the anode, but as we discussed earlier, it does not have to be. The line diagram is just referring to what's hooked up to the negative terminal of our device. For our example, that would be zinc solid as the electrode, and then phase boundary, because all the other chemicals are in a completely different phase, right? Aqueous species. So we could either write zinc sulfate in full, or it is actually okay to just write zinc 2 plus aqueous, since that's the actual electroactive species in those half reactions that we drew earlier. Now that, of course, is only half the cell, so let's get to the other half. Back to the general format, I am going to draw, after the words other chemicals, 2 solid lines. And this just represents our salt bridge. And we'll make a note in parentheses, we don't specify the contents. Don't specify contents. In other words, at no point will we actually write KCl in this kind of notation, or any species that happen to be inside of it. After the salt bridge, we will write other chemicals again. Other chemicals, phase boundary, and then electrode. Although, as you can probably guess, we are now referring to the chemicals in the electrode hooked up to the positive terminal. And so back to our example below. After that zinc sulfate, or just zinc 2 plus, just salt bridge, we don't specify KCl, and then we write the chemicals that are in solution on the positive terminal side. That would be either copper, sulfate, aqueous, or again, we can just write the electroactive species, which is the copper 2 plus ion. Then phase boundary, and then the copper solid electrode itself. And that is a much simpler way of representing this entire cell right here. And you need to be able to interpret it both ways. I should be able to put a drawing like this on a page and ask you to figure out the line diagram, or a more difficult exercise, I should be able to give you the line diagram and have you redraw all of this. The only thing that you wouldn't be sure about is what's in the salt bridge. I would have to write that somewhere else, like draw this cell with a KCl salt bridge. Now, at no point in our example did we use this comma that we made a note about. So let me show you a more complicated example of a half cell. So here we have an electrode that consists of two different solids. It's a slab of copper metal, but with some platinum particles decorating the surface. And this is placed in a solution that has two different cations, Fe3+ and Fe2+. Now this time for the electrode, we have two different solids. And even though they're both solid, we're going to put a phase boundary between the two. Because while they are the same phase technically, they have distinct boundaries between them. In this drawing, it's very clear where the platinum is and where the copper is. They're not well mixed like a solution. In contrast, the iron 3+ and 2+ ions are well mixed. Not only are they both aqueous, but there is no distinct boundary between the two species. And so we use a comma to differentiate between these two aqueous species, but we use a solid line, i.e. a phase boundary, to distinguish between these two solids that are not well mixed at all, but have clear boundaries between them. And then we use yet another phase boundary, the way we did in the prior example, to distinguish platinum solid from these aqueous species. Now you might be wondering, how did I decide which solid would go all the way to the left of this notation? And the answer is copper is the larger component of the electrode. But in all honesty, I don't care so much about your ability to choose between which solid goes all the way on the left, so much as your understanding of why you need a phase boundary between them even though they're both solids. Whereas with the two aqueous species, we use a comma instead. Now after this comes a clicker. It's actually the first of three that build off of each other and relate to this cell. I call this part Clicker Fest. We will of course do it in Zoom, but if you want to see the three clickers, you can get them in Canvas slides. We'll definitely spend a good chunk of our Zoom session doing this part of the lecture.